Hello, everyone. So welcome back to this third day of DAOISM conference. This morning, we'll start with Thomas Oberlin. We'll talk about deep priors for approximate posterior sampling in imaging inverse problem. You have 30 minutes.
Thank you. Good morning, everyone. And thanks to the teams of Orion B and DAOISM for organizing this nice workshop. So I will present some work which was essentially made by my PhD student, my former PhD student, Maud Bicard, that I co-advised with Marie Chabert from IRIT in Toulouse and Florence Génin and Christophe Latry from CNES. So the context, there has been a lot of talks about this already, but I will take a few minutes to give my notation and some examples. The context is imaging inverse problems. So we are given an observation Y, and we are looking for a target image X. And we assume that we know the forward model, F, the degradation or forward model. And there is some noise term, of course. So this includes a lot of different problems in astronomy, astrophysics, or in other areas. So I gave a few examples here. On the left, it's compressed sensing in the Fourier domain. Here, this is the inverse problem in electroencephalography. So it's not pure imaging, but let's say it's imaging. And this is the inverse problem in geoscience, in seismology. Okay, and you know, of course, a lot of different problems related to astronomy and astrophysics. So how to find X given Y? We have two different ways of seeing this problem. The first one is on the optimization point of view, on the operator point of view, where we try to invert F as an operator. And we need some regularization R because F is most of the time singular or at least bad condition. The other way is the Bayesian formulation. There has been a lot of talks already about this, where we try to characterize or sample from the posterior distribution P of X given Y. And what is specific about imaging inverse problem is that in many cases, it's not sure the case, but in many cases, and it will be the case here, the forward operator is simple. That means that in most of the cases, it's even linear. And at least we have fast algorithms to compute it. So there is no problem such as in simulation-based inference, where we have a huge model that takes a lot of time to run. But the solution we are looking for is very complex because it lives in a high-dimensional space, and there are a lot of invariances that makes the solution very hard to characterize. So the main issue here is to design a proper regularizations or prior distributions. So, of course, there are a lot of different ways of tackling this method. I already talked about variational methods against Bayesian. We can also differentiate the methods between model-based methods or data-driven ones that will use machine learning or deep learning. And among machine learning methods, we can either rely on machine learning end-to-end to perform the inversion directly. So try to learn a mapping Y to X, or use it only for regularization. I call this deep regularization. And then the last point is either we are looking for a single estimate or a distribution that will allow for uncertainty quantification. So here we will be in the framework of model-based inversion with learned regularization and posterior sampling, or at least approximate by posterior sampling, to be able to derive uncertainties. Okay. Of course, there is a lot of literature about all of this. I will not detail everything, but even before deep learning, there were deep regularization methods. For instance, machine learning regularization. For instance, with dictionary learning. Then, since the rise of deep learning, there are mainly two ways of doing of learning the regularization of the prior, either implicitly with denoisers or explicitly with generative models. And there is a link between a denoiser and generative model. A nice way of seeing this is the 3D formula. And then, how can we use machine learning to in a posterior sampling framework? There are mainly two ways of doing this. There is a lot of works on MCMC with learned denoisers. And there are also all the literature about diffusion models. There are a lot of different methods that use diffusion models as prior in posterior sampling framework. Okay, so our method is neither, it has some links, but it's neither a denoiser or a diffusion model. It relies on variational autoencoders, and I will try to explain with this, starting with what is a variational autoencoder. It's simply a latent variable generative model. So we are given a prior P of Z. Z is a latent variable, and we learn to map Z to X with some parameter theta. And most of the time we made Gaussian assumptions. So the prior is simply this probability distribution, and the generative model, P theta of X given Z, is a Gaussian parameterized by some guys that are learned by a neural network with weights theta. So D is the mean, and sigma is the covariance matrix of the Gaussian distribution. This is the generative model. And in VAE, we approximate the posterior distribution, P of S of Z given X, by a variational distribution, Q, which is also chosen to be Gaussian with some mean parameterized by an encoder neural network with weights phi, and a diagonal covariance matrix, which is also given by the same network with weights phi. And at the end, we learn both weights phi and theta by maximizing the elbow, the evidence lower bound, which writes like this. I will not detail it. We can go back afterwards if you have some questions. But there are several assumptions that can be made on the decoder, and more particularly on the covariance matrix of the decoder. Most of the works assume that the decoder just outputs a mean, D, theta of Z. So this is the image, the mean image, but there is also, since the decoder is a generative model, it's probabilistic, and there is also a covariance. But most of the time, the covariance is just parameterized by a single scalar, gamma. And even in some works, gamma is fixed, which is a very bad idea, because if you do that, you end up with a posterior collapse and you don't have a good generative model. But it's also possible to learn gamma along with the other parameters of the neural networks. And it's possible. But it's more realistic to have not a full covariance matrix, but at least a covariance matrix that is able to model the different correlations between neighboring pixels. And this works propose to do this, and it works quite well, and it relies on Cholesky factorization. Okay, and there is a trade-off between those two to just consider a diagonal covariance matrix, the same assumption as we made for the encoder for the variational distribution. Okay, this is important because I will go back to this afterwards. And then there is a terminal method that has been proposed almost 10 years ago to use a VAE to regularize an imaging inverse problem. So we call this MapZ because it's a maximum a posteriori in the latent space of a VAE or other generative model with a latent variable. So this is a two-step method. First, you need to learn the VAE on a data set of target images. So you need to have a data set. Define? VAE, variational autoencoder. Sorry. So it's a generative model. And once you learn the VAE, you can keep it fixed and use it as a prior to solve the inverse problem, the imaging inverse problem, so trying to find x given your observation y. And you can do this simply by minimizing this term, which is the usual thing, except that here we assume that the decoder, this is important, we assume the method assumes that the decoder is deterministic. That is, x is exactly the decoding of z. Okay, which is the limitation because it leads to search for the target images in a manifold which does not fully cover in general the space of all possible images. Other limitations are that in general VAEs or generative models are more expensive to train than denoisers. They are bigger networks, they require more data. And it's also a point estimate method. We don't have access to uncertainty quantification. So building on this method, we propose the variational-based latent estimation, where instead of computing the map, we approximate the posterior distribution, P of x given y, using the variational autoencoder. And actually, we don't approximate only P of x given y, we also include z. So it's a joint posterior distribution where we are looking for the posterior of the distribution of P of x and y given the observation, x and z given the observation y. And how do we do that? It's a standard variational inference machinery. We minimize the Kullback-Leibler divergence between the true posterior and our approximation, Q psi. And how do we choose Q psi? We go back to the VAE. So we build a distribution this way. We have part of the distribution which is in the latent space, Q of z, and it's parameterized by two parameters. So it's a Gaussian centered on z bar that we will estimate, and with some diagonal covariance matrix given by the parameters A. So this is the part in the latent space, and then there is also a part in the image space. So Q of x given z is also a Gaussian. It's centered in d of z. So the decoder will map the most probable latent variable z to d of z, but we add some small bias, nu. It can help sometimes. And more importantly, we scale the covariance matrix. So if you remove this term, you go back to the covariance matrix of the VAE. So it's something that is fixed, that has already been learned. And here we modulate this with the parameter B. So at the end, we have two parameters, z bar and nu, that will localize the most probable image in the latent and image space. And we have two other parameters that will modulate the uncertainty, that will modulate the size, the width of the two distributions. And how do, this is a graphical summary. So this is a generative model, a neural network that outputs an image and a covariance matrix. This is a latent space, so we are looking for those two parameters that give you the volume in the latent space, the distribution in the latent space. This here, the line here is a push forward measure of Q. So it lies in a manifold in general because the generative models does not go. Yeah. Okay, it's only a part of the space, and to augment this, there is another part of the distribution here in blue. And how do we optimize everything? So we have four parameters, and actually we use the same algorithm as that one was proposed by Kingma and Velling 12 years ago when they introduced variational autoencoders. It's called stochastic random variational base. It's quite simple to implement. It's compatible with backpropagation, and the libraries here, PyTorch, does most of the job. The only thing is that we need to initialize well the parameters. And actually, the best way of initializing them is to match the prior of the VA. Okay, so there are different variations around this VBLE method. So here I recall the full variational distribution. And we can simplify it first by considering nu equals 0. But it's also possible to assume that this part of the variational distribution is a Dirac. So this makes the decoder deterministic. And it amounts to model all the uncertainty in the latent space. We can do the opposite. In that case, we have all the uncertainty in the image space. So we denote these methods as VBLE-Z and VBLE-X. And then if we take two Diracs, we end up with a point estimate method, which is a MapZ that was presented a few minutes ago. Okay, there is another detail related to the architecture. Actually, we don't have good VAEs that have almost no reconstruction error, and this is a problem. And in this work, we propose to use instead compressive autoencoders, so neural networks that were trained for image compression. So this is another part of the literature, but actually, state-of-the-art CAEs are very similar to hierarchical VAEs. And the good thing is that they are lightweight. We have pre-trained models because it's quite popular in the literature of image compression. So I won't go too much into the details. CAE is a variant of VAE, let's say. Now I will present you some results that are not related to astronomy or astrophysics. It's satellite imagery, but from the Earth. And here is the experimental setting. So we use pre-trained CAEs from a library that we fine-tune on a data set. So I remind you that to do deep regularization, you need a data set of target images. In astronomy or astrophysics, it can be challenging and it often relies on simulation. But in Earth observation, we have campaigns that acquire very high resolution images by airplanes. For instance, here we consider a data set of images with 5 centimeters of GSD, so ground sampling distance. That means that 1 pixel represents 5 centimeters on the Earth. And by downsampling this, we can create images that are almost perfect, that contain almost no blur and no noise. That will be our target image data set. Okay, there is a trick about multi-rate CAE, but I will skip the details. We will compare VBLE-Z, so everything is modeled only in the latent space, and VBLE-X-Z with diagonal covariance matrix. We consider a position Gaussian noise because it's a standard model for satellite images. So we need to adapt the likelihood. It's not only a least squares term. And when I display a result from VBLE, it will be an MMEC, so an empirical mean of 100 posterior samples. Okay, and we'll consider image restoration, that is image deconvolution and denoising. Single image super resolution, that will try to add a zoom by a factor 2. All will be for the Pléiades satellites, so it's a high resolution French satellite. It's panchromatic images, there is only one spectral band. And we also consider in painting, it's more like a toy example, but it's interesting. We consider different image quality metrics. I guess you know PSNR. SSEM is another metric, and LPIPS is a more recent perceptual metric that is based on a pre-trained CNN classifiers. It's widely used in image processing and especially super resolution. And we also have a metric to characterize how well the uncertainties are, the predicted uncertainties. So we call this ICP. So the ICP alpha is a per pixel coverage probability that will count the proportion of pixels for which the true errors is in the alpha quantile on the predicted error. Okay, so the goal is to have ICP alpha the closest as close as possible to alpha. And we compared our result with different methods. So first, direct inversion. So simple CNN that will take the degraded image and output the target image. We have a small one and a bigger one. So this is the number of parameters. Then we have deep regularization with point estimation, either with a denoiser, brunette, or with a diffusion model. Note the difference in the number of parameters when using diffusion models. And we also consider deep regularization with posterior sampling, either with a denoiser, the method is termed PNP-ULA, or with the same method as before, but we run it 100 of times to have 100 samples. And these are the results. I can go back later if you want, but in a few words, our method is not the best. If you just look at a single image, plug and play with a denoiser, so this method is very good, and it's quite efficient in computation time. Okay, our method is quite okay, but it's not better at least. And even direct inversion are quite okay. Even this one, which uses a very small neural network, it's okay. But okay, here are some visualizations, but it's not very clear the different differences, especially at the screen. For super resolution, you can see some artifacts, and the artifacts are different for the different methods, but you really need to zoom in. What is more interesting is the results among the posterior sampling methods. So here we evaluate image quality, with the first three metrics, but also the quality of the samples and their ability to effectively capture or estimate the uncertainty. And here it's more interesting. Depending on the problems, I will take super resolution because it's a harder problem than just a deconvolution. For super resolution, in terms of image quality metric, DiffPeer is the best one. But again, remember, it relies on a huge diffusion model. And its computation time is prohibitive. And VBLE is very similar in terms of image quality, just a bit less, but it's really faster. And more importantly, we have the best ICPs. So among all those methods, it's the method that best predicts the uncertainty, at least with this way of estimating. Okay, and the differences between VBLE Z. So in this method, we only model the uncertainty in the latent space. And you see that the ICPs are really worse than here. The image quality is okay. It's even sometimes better than here, but the uncertainty is really less captured, let's say. This is an example. So how can we visualize the uncertainty and can it help the final user? So this is a ground truth. This is observation. So blur and subsampling by a factor 2. This is the result of VBLE XZ. So this is the MMSE, the mean among some posterior samples. And here you can see two samples. They are sharper. They are a bit more noisy, but they are sharper. And if you, thanks to these samples, we can produce some error quantile and compare it with the true error between the ground truth and the MMSE. And you see that it correlates quite well. Okay, and it's also the case for DiffPeer 100, but it's not the case for PNP-ULA. Okay, this is an example on a real Pleiad image. So it's harder to compare the methods, but let's say that it's consistent with what we expect. So this again are the error quantiles, the per pixel error quantiles. So of course, first they are edges detectors, so they are higher when they are high frequencies. But we can also see some details related to very small details, such as pedestrians here or small lines in the image. This is a small ablation that compared, but it's from another data set, but it's still interesting. It compares the different variations around VBLE and compare it with the map Z. And we have the same results as before. So in terms of image quality metric, other variants than VBLE-XZ are good, such as the VBLE-Z. But when looking at the ICPs, the best one is this. So it really means that to capture all the uncertainty, to approximate well the posterior distribution, we need a joint modeling in the image and the latent space. Okay, so this is the end. I'll try to present you VBLE, which approximates the posterior sampling of an imaging inverse problem based on a pre-trained variational autoencoder or compressive autoencoder. The uncertainty is jointly modeled in the latent and image spaces. And it achieves a good performance complexity trade-off. So it performs on par with state-of-the-art methods based on diffusion models, but it's really lightweight and it can be deployed in real applications such as satellite images. So there are a lot of perspectives, but I would say that an interesting one would be to better use the posterior samples, because here we only showed per pixel credibility intervals or error quantiles. And it's really a small part of what we could do with the posterior sampling method in high dimensions, but it's not easy to do. And as far as I know, there is not a huge literature dedicated to this problem, either in image processing or other areas in statistics. So there are two journal papers that summarize and detail the method. If you want to have a look, and this one is in prep, and it's to apply demosaicing. So for color imaging, it's with VBA. Thank you, and I will be happy to answer any questions.
Are there any questions?
So I have an easy question. So what is the size of the image?
It depends, because the original size is like 20,000 by 20,000 pixels. But of course, we crop the images. And we have, since our architectures are fully convolutional, we can input any size. But the limitation is the memory of the GPU. So here we crop the image by a size of 512 by 512.
Okay.
But if you have a bigger GPU, you can have bigger crops.
And I didn't understand. So you have autoencoders, and so you make a distinction between variational and compressional autoencoders. But does it mean that the latent space in one is bigger than the other one?
It's a good question. The size of the latent space. Traditionally, variational autoencoders have small latent spaces. If you want to have a good generative model, unconditional generative model, you need this. You need to summarize the information in the lower dimension. But actually, if you do this, you will have a higher reconstruction error, because the range of the decoder of the generative model will be a manifold of small dimension, which is essentially the dimension of the latent space. And the kind of VAEs or CAE we use, the latent space has the same size, approximately, as the image space. So it's an image compression, but it's not a compression in terms of latent space compression.